Hey there everyone, it's your math teacher Mr. Boyden back at it again, and today we're going to be talking about the Pythagorean theorem and its converse. Alright, so we learned way back in middle school, maybe even elementary school for some of you, about a squared plus b squared equals c squared. Essentially, if you're already really good at that, today's going to be a review with one new little twist. Okay, so everybody knows how to recite that. We don't always realize what it means. First thing to realize is, what are a, b, and c? Well, they apply to a picture like this one down here where we have a triangle. And the important thing to note is that this side right here is going to be C. Now that side is called the hypotenuse. And one thing that's important about that we don't always do a good job of teaching is that you can only have a hypotenuse if you have a right triangle. Which means that this must be a 90-degree angle, and the hypotenuse is always the side that is opposite from the 90-degree angle. Or if we draw a line through the shape, that's always going to lead us to the hypotenuse, and that is always C. So I'm going to put a little H right there, which means that these two little guys are what we call legs. And notice they're added together, and when we do addition, like 3 plus 5 and 5 plus 3, the order doesn't matter. So which side length is A and which one is B? It doesn't matter. The only thing that matters is that you put A and B on the legs. Now, what a lot of students prefer, because it makes it easier to think about, is if you consider A to be the shortest side and B to be the medium side and C the longest side, that would be fine, okay? In general, that's a nice little rule of thumb. Doesn't work 100% of the time, but especially if you're just learning this, it might be a little bit easier to think about. Okay, so what we're going to do today, we're going to make sure we know how to find side lengths. That's the purpose of this. A, B, and C are sides. Has nothing to do with angles. We're going to be finding side lengths. Before we do that, we're going to talk about one little arithmetic thing that you need to know how to do in order to express your answer clearly, and then we're going to deal with the converse as well. So let's get to it. Y'all, first thing we need to know how to do is how to simplify a radical. So we're going to do a few examples together. I'm going to start with root 8. And sometimes when you get done with a question, it will ask for simplest radical form. Okay? Simplifying radicals, simplest radical form. And what they mean is, don't type this in the calculator. I mean, certainly we know how to type it in the calculator. I can type that in right now and get 2.8, but that's not what they want. So if they want you to simplify it, here's one method for how to do that. Okay, you could do what's called a factor tree. So you're looking for numbers that multiply to be 8, like 4 times 2. And we're going to keep going off of these. 4 could be written as 2 times 2. 2 could be written as 2 times 1, but we don't want to use 1 in these because we want the numbers to get smaller as we go. Now, folks, if you can make this factor tree, you can simplify your radicals. Here's what you're going to look for. You're going to look at the ends of the branches. I have 1, 2, 3 branches. At the end of each branch, you're going to look for numbers that are equal, and you're going to pair them up. So I'm going to make a little pair right here. And so I make a pair, that's 2 times 2, that's 4, but since they're a pair, I'm just going to write the number. Now, this number right here, I'm going to call that a loner. I called this a pair, that's a loner. It's left over, it has no one to dance with. And so if you have a loner, you're going to put a little root and you're going to put a 2. Now that's a little bit of a corny way of understanding this. The mathematical reason that works is we said 2 times 2 is 4, so what that really is root 4, and that's root 2. And then the square root of 4 is 2, so we're rewriting it. Okay, so that's the mathematical reason it works. If you want to do like the partner and the loner thing, that works fine as well. So let's try square root of 50 then. Okay, and if you want to pause and make your own factor tree, awesome. If you want to watch, okay, that's fine too. Make sure your notes are wonderful. Okay, I'm going to break 50 down. The first thing I see is 5 and 10. Y'all, there's different ways to do it. Some people see 25 and 5. Totally fine, doesn't make a difference. So just do whatever feels good to you, okay? 10 can continue to break down into 2 and 5. And so what I have then, I have a pair of 5s, and I have a loner 2. And so the 5 gets written, my loner gets a root. Done. That's a simplified radical. One more. Oops, I wanted 108. Let me do a redo there, y'all. Okay. So on this, I would suggest you now pause the video and try it on your own. We've done a couple of them together. Pause the video and try it on your own. Okay, first thing that jumps out as me is that's probably divisible by 2, which would leave us with a 54. 54 is divisible by 2, which gives us 27. 27 breaks into 3 and 9 breaks into 3 and 3. Now I'm going to start looking for my pairs. I got a pair of 2's at the end, so write a 2. I got a pair of 3's at the end, so write a 3. And I got a loner 3, So 3 with a root. Now some people will leave it just like that and they'll say 23 root 3, but folks, these are multiplied, okay? So be really, really careful. They're not added. It's not 23. 2 times 3 is 6, so this is 6 root 3. Okay, there's 3 examples. So when we say simplified radical form or leave your answer in exact form, something like that, this is what we're looking for. When we get to the end of the question, this is going to be your final set of steps. Now let's go to actually answering some questions now that we know that. So on this one, I've got a triangle. It's a right triangle. Remember, the Pythagorean theorem only applies to right triangles, so this works just fine. And so I'm going to remember that's a squared plus b squared equals c squared, and I'm going to start plugging these in. Now folks, probably what's most important is c squared, because that's always the hypotenuse. Hypotenuse is over here, so that's where my x squared is going to go. For a, I'm just going to pick the lesser of these two. Okay? So 20 squared plus 21 squared. Now, little things that people miss. Some people forget to put the squared. Don't forget to put the square. That's silly. And some people forget that squared is different than a square root. Okay, so this means 20 times 20. Use a calculator if you need to. That's 400. And 21 times 21 is 441, and that equals x squared. And sometimes people get a little bit too excited here about this little x squared, but y'all, what we're going to do is what we know how, and we know how to add 400 and 441. So that's 841. And then we're going to take a square root of that, and that's really hard to do. So what I'm going to do is I'm going to check in the calculator, and I'm hoping I get a whole number. And it turns out that I do. Now, if I didn't get a whole number, I'd need to start breaking it down in a factor tree. But I got 29 when I did that, and so that's x. Now, we should always check and see, is our answer reasonable or is our answer ridiculous? Okay, that's 21, that's 20. 29, yeah, it looks longer. I think that's reasonable. Would 841 have been reasonable? Probably not. If you have 20 and 21, 841 is probably a wee bit on the big side. That's why we had to take that square root there. Okay, so that one is 29. Let's try another one. Okay, here's our next one. We're going to find x. It's a right triangle. Why don't you pause the video and try to do, at the very least, the setup by yourself. Okay, and once you get to here, make sure you have the 12 by itself. 12 is c because it's the hypotenuse. If you do not put the 12 over here, you're toast. There's no way you're going to get through the rest of this because your setup is wrong, okay? So be really, really careful. Now we're going to go through and start simplifying. So x squared plus 100 equals 144. And then I'm going to subtract 100 on both sides. And I'll actually write that in, minus 100, minus 100. And I get x squared equals 44. I take a square root. Oops. So 100 x squared equals 44. Take a square root on both sides, and I get x equals square root of 44. Now I can try typing that in the calculator, but I get a decimal. And I want to answer this in radical form. So how am I going to do that? I need to make a factor tree. Now folks, again, pause the video and try this on your own. We've done 3 examples together. I bet you can get this one without any help at all. Then watch the video and see if you got it right, okay? So the way I do this, and there's a couple ways to do this, y'all. I do it as 2 and 22, and I break the 22 into 2 and 11, and the 11 doesn't break up. Now, some people do it a different way. And so I'm going to show that as well. Some people do 4 and 11, and they break up the 4 into 2 and 2. Here's what I want you to notice. 2, 2, 11, 2, 2, 11. You end up with the same factor tree in the end, even though in the middle it's different. So they're both obviously fine. Okay, so pair of 2's, so we write a 2. We have an 11 as a loner, and so I get a root 11 right there, and so that's what x is in simplest radical form. Okay, let's do a little bit more of a real example. Okay, let's do this one for baseball. In baseball, the bases are 90 feet apart. It applies to fast pitch as well, by the way. So in baseball, you can do something called stealing a base. So if we have a little person here on first base, sometimes they will take off even when the ball is not in play and try to get to second base. And that means they have to run a distance of 90 feet. And it's known in baseball that it's a lot easier to steal second base than it is to steal third base. And so let's talk about why. Now usually the pitcher pitches, the ball ends up down here, and in order to get the runner out, they have to throw the ball down to second base. Or they're going to throw it to third base, depending. Now if they throw it to third base, that's 90 feet. But if they throw it to second base, how far is that? Okay, let's examine that question a little bit. So we know the distance to the bases is 90. it's a right triangle, and we want to know how far does the catcher have to throw the ball. So this would be a really good chance for you to try another example all by yourself. Go ahead and pause the video, set this up, see if you can figure out what x is. Okay, here's my setup. Okay, and I'm going to square these, and so I get 8100 plus 8100 equals x squared, so 62, oh, excuse me, 16,200 equals x squared, square root, square root. And then here's where it gets a little funny. Do we want to do this in a decimal form or in a radical form? Okay, and they don't tell us in the question. So here's what I'll tell you, y'all. If it is a real world question, generally it's appropriate to use a decimal. If it's just a mathy question like the ones before they were just triangles, there was no context to them, then we want a radical or an exact form. This one we could type in the calculator though. Okay, so when I do that, I get 127.3 feet. So back to the question. Why is it so much harder to steal third base than second? Well, it's because of this. When the catcher has to throw the ball to second, the ball has to travel 127.3 feet. But when they throw it to third, it only has to travel 9 feet. So it's a much more difficult throw to throw the ball to second base than it is to third. So if you have an easier throw, you have a better chance of beating the runner, and that's why it's so much harder for the runner to make it to third without getting out. All right, now that we've got the basics of the Pythagorean theorem down, we can move on to talking about the converse of the Pythagorean theorem. And so what that's going to be used for is determining if a given triangle is right, acute, or obtuse. Now, we said the Pythagorean theorem only works for right triangles. So what that means is we're actually going to break the Pythagorean theorem and see what happens as a consequence of that. Okay, so this is a really typical question that we're looking at here, where you have side lengths of 6, 11, and 14. We have to decide if that triangle is acute, obtuse, or right. And so one way to do this is to actually draw a triangle that maybe kind of sort of looks like that. And so what I'm going to notice is that I have 6 and maybe 11 and 14. You go, well, it looks like a right triangle. Well, but what if it's 89 degrees? Okay, so maybe it's not exactly right. We have to test it. Here's what we do. If we were going to do the Pythagorean theorem, we would know that that was a squared plus b squared equals c squared. And so we need to decide what numbers would we pick for each of these spots. So which number would you pick for a? Generally, it makes sense to pick the smallest one. Okay, so 6 squared plus maybe 11 squared equals 14 squared. Now, if you change the order on the 6 and the 11, it's not going to hurt you because it's addition, right? It's commutative. But if you pick the wrong number for c, it's trouble. So always the largest number goes for c. Okay, now let's simplify these. That's 36 plus 121 equals, and make sure you don't actually add them together yet because we need to incorporate the 14 squared. That's 196. This now says 157 equals 196. Okay, first of all, is that true or false? Pretty clearly that's false. 157 is not equal to 196. So we have acute, obtuse, or right. Can you tell me what the answer is now? Or could you tell which of those answers is definitely wrong? Now remember, we said the Pythagorean theorem will always work for a right triangle. And it didn't work. So it is not a right triangle. Okay, so that's out. Now we have to interpret this result and see what it means. So the numbers are not equal. Well, okay, why are they not equal? What I notice is that the number that came from c squared, is it too big or too small? It's bigger than 157, so that tells me it's too big. So folks, here's what's happening. That means you have to think about what would be going on that would make this number too big. It means, and watch how the red line gets longer as I do this, it means that something like that is happening, okay? So if that side gets longer, it's going to push this angle open. And so if this number is too big, take a look at our picture now. What kind of triangle is it? This is an obtuse triangle. If the number is too big, it's going to be obtuse. If the number that is corresponding to the hypotenuse is too small, then it's going to be acute. Let's do another example, maybe 2 more examples until we get this. So guys, I'm just going to make up new numbers for these right now. Okay, let's try 6, 8, and 10, and we can do a new calculation right here. Please pause the video. Pause the video, try this one on your own, try to interpret your answer. Okay, here goes. 6 squared plus 8 squared equals 10 squared. That's 36 plus 64 equals 100. And folks, I'm going fast, but I have a lot of experience doing these, okay? So if you need to slow down, use a calculator, please do. Okay, and then this adds up to 100 equals 100. No, don't make that look like a 6. That's 100 equals 100. Guys, it worked. So what does that mean? If it worked perfectly, remember, Pythagorean theorem only works for right triangles. So this is a right triangle. Let's do one more example. Okay, I'm going to do that over here. Let's do an example where we have, let's try 6, 7, and 8 as our side lengths. Okay, so again, pause the video, try it on your own. 6 squared plus 7 squared equals 8 squared. So 36 plus 49 equals 64. Oops, sorry, it doesn't look like a 64 really. Okay, and if 36, we have a 36 and a 49, I'm going to add those together, and I get 85. So 85 equals 64. And remember, we're always looking at this number on the right. That number is too small, which means if I make this shorter, it means that that angle down here had to get smaller. So what does that tell us? That tells us this is an acute triangle. Okay, and guys, that's the only 3 things that can happen. The number that corresponds to C is too small, it's too big, or it's just right. Hey, it's just right. It's right. Okay, guys, that's all for today. Okay, we've gone over the Pythagorean theorem, how to simplify radicals, and the converse of the Pythagorean theorem. That's really all there is to these for now until you get to like pre-calculus and start doing law of sines, law of cosines, and adding on to these a little bit. Okay, so that's going to be all for today. Hope you enjoyed the video, and we'll see you next time.